In today's video, we will learn about Newton's law of universal gravitation. Newton's law of universal gravitation states that if two particles with their own individual masses are separated by a distance, a gravitational force acts along a line joining them with a magnitude. And we can measure this force by taking the capital G constant times the mass of object 1 times the mass of object 2 divided by the radius squared. And we see that the constant for our capital G is equal to 6.673 times 10 to the negative 11th. When we lifted an object to a certain height, we said the object had potential energy. However, when an object is far away from Earth's surface, the potential energy we measured as mass times gravity times a change in height cannot be applied, since our acceleration due to gravity varies at different altitudes. So when an object with mass is displaced a large distance away from Earth's surface, we can calculate the gravitational potential energy, which is equal to our negative G constant times the mass of Earth times the mass of the object divided by the total radius. And in order for an object to escape from Earth's atmosphere, a particular velocity has to be achieved. We call this velocity the escape speed, and can be calculated by taking the square root of 2 times our capital G constant times the mass of Earth divided by the radius of Earth. And so we see that velocity therefore is independent of the mass of the object and only depends on the planet's mass and its radius. In our first example, it states that objects with a mass of 200 kilograms and a mass of 500 kilograms are separated by 0.4 meters. Find the net gravitational force exerted by these objects on a 50 kilogram object placed midway between them. So to the right we see a quick illustration of the interaction between our three objects. We see that each object is defined by mass and is separated by a distance of 0.4 meters between our outside objects and a distance of 0.2 meters between our middle object in either the outside or inside direction. And let's label this object M1, this object M2, and our last object M3. So we see that gravitational force is equal to capital G times the mass of one object interacting with the mass of a second object times the radius squared. So since we have a force of object 1 acting on object 2 and a force of object 3 exerting a force on object 2, we'll have multiple forces. So if we sum up our forces, we'll see that capital G times the mass of object 1 times the mass of object 2 is equal to, and divided by radius squared, minus the force exerted by the mass of object 3 on the mass of object 2 divided by its radius squared. And factor out our G constant, our mass of object 2 divided by the radius squared times the difference of the mass of object 3 minus the mass of object 1. And if we plug in the values, we can solve for our net gravitational force. So capital G is equal to 6.67 times 10 to the negative 11th times the mass of object 2 of 50 kilograms times the mass of object 3, which is 500 kilograms, minus the mass of object 1 of 200 kilograms, divided by our radius squared, which is the distance from object 2 in either direction towards object 1 or object 3. So we see that our radius is 0.2 meters squared. And when we calculate this out, we'll see that the net force is equal to 2.50 times 10 to the negative 5th newtons, acting in the direction towards our 500 kilogram object, or M3. In our second example, we're asked to determine the speed of the Hubble Space Telescope orbiting at a height of 598 kilometers above the Earth. Assuming that the radius of Earth is 6.38 times 10 to the 6 meters, and that the height of the telescope above Earth's surface is 0.598 times 10 to the 6 meter. So we're asked to solve for our orbiting velocity. And our velocity can be found by taking the square root of our capital G constant times the mass of Earth divided by the orbital radius of the satellite. And so we can find our orbital radius by taking the radius of Earth plus our satellite's altitude or height above Earth's atmosphere. Our given Earth's radius is equal to 6.38 times 10 to the 6 meters, and that our altitude of our satellite above Earth's atmosphere is equal to 0.598 times 10 to the 6 meter. And we add this together, see that the radius of our orbit is equal to 6.98 times 10 to the 6 meter. Now that we know the radius of our orbit, we can plug it in for our radius into our equation. And now, since we have all our values, you see that the capital G constant times the mass of Earth, which is 5.98 times 10 to the 24th kilogram, divided by our radius, which is equal to 6.98 times 10 to the 6 meter. And when we take the square root, we'll see that our orbital velocity will be equal to 7.56 times 10 to the third power meters per second.